In this video we're going to take a look at the ROPME challenge on Hack the Box. It's a hard pwn challenge and the description says, can you pwn the service and get the flag? I'll just note before we get started, this challenge, although it's rated as hard, it's actually a lot easier than most or a lot of the challenges that we've done so far which were rated as easy, and I would say that's, as I've mentioned previously, is largely due to the fact that these challenges have been retired pretty recently, and the people who find them easy, who have solved them, have probably done all the older challenges, so that kind of makes sense. But just worth bearing in mind, don't be off-put by the difficulty rating here. It's actually going to be not going to be too difficult for us to solve it. So as usual, we'll start by downloading the files, and we'll go and do our basic file checks. So we'll copy this over to our local directory. So as usual, begin by checking the file type, and also as usual we'll see it's a 64-bit LSB executable. It's dynamically linked, so if it needs to get functions like system and puts and write and things like that, it's going to call out to the external libc library. And it is not stripped, so the symbols haven't been stripped. It just means that debugging and reverse engineering it can be a little bit easier. I don't see pi enabled here as well, so well, let's just run checksec also. We'll do checksec ROPME. And yeah, there's no canaries, no pi, so every time this program loads, the addresses are going to be the same, which means whenever we check the addresses in Girdra or IDA or Radar or GDB or wherever, we're gonna be able to just copy those addresses directly into our code, and we'll be able to use those same addresses against the server. However, NX is enabled, so even if we find a buffer overflow here, we're not just going to be able to inject code onto the stack and execute it. So we can kind of get an idea what we're going to have to do just from the file name alone. We're going to need to do use some ROP gadgets to actually exploit this binary. We could check the strings as well, do strings-n10, and we can see there's not too much functionality here. We don't have much text saying ROPME outside, how about dar, and I can't actually see any other input there. Let's make the program executable and try to run it. And it's taking some input off us, so we can put something in there, and then the program just exits. So let's run that again with ltrace, and we'll see that it's actually calling fgets. We can say hello, and it's trying to read in 500 bytes from us. So we could keep increasing the number of characters we're entering to see if we get a buffer overflow here, but let's just open this up first in Girdra to do some static analysis, and then we'll go and try and find the offset to the buffer overflow in GDB. So open up Girdra and we'll create a new project. Double click on the file once you've gone through all the painfully slow project creation screens, and again analyze, yes, just OK to everything. And here we go, we've got to our code here. It's not stripped, so we can just go straight in and have a look at our main method. And the main function doesn't actually do too much. We can see we have the buffer declared here, 64 bytes, 64 chars, and then we have the fgets call, so it prints out this output with puts, and then it reads in 500 bytes into our 64 byte buffer. So there's a clear buffer overflow there. There's no other functionality here in a program that's not going to any other functions. So I mean, we have seen in previous challenges where we've had like a ret to win style solution where we need to return to some kind of function in the program which isn't normally called, but if we go and have a look for strings here, we've already seen whenever we ran strings there really isn't much else in the program. We can go and have a look through the functions here, but yeah, apart from the libc functions that we have available to us, there's really not too much. So let's I'll keep this open, but let's minimize this. Let's go and verify this buffer overflow. We'll go and find out what the offset is to the return address. So I'll open GDB pwn debug and pass in ROPME. We can have a look here at the functions as well. Again, we know we don't have too much. If we wanted to, we could disassemble main and have a look at the code here, set up any breakpoints we want to, if there are any functions we wanted to grab, so we know like what's the address to the puts function, to fgets, libc start main, etc. So we can go and grab our functions here, because this isn't gonna, we don't need to do pi base and stuff like we've done in some previous challenges because pi is not enabled. What else can we do here? Just if you watch all my videos, you'll be sick of seeing this, but we can check help here. We can do help breakpoints, for example, and get all the documentation, because there's quite a lot that you can do within pwn debug. We can also type pwn debug, type it correctly, it'll help, and that'll give us a list of different functions and plugins that we can call from within pwn debug. So for example, rather than just going outside, we can actually just call ropper from inside here and get the addresses of our ROP gadgets. So yeah, I think that's good. Let's generate a cyclic pattern. We'll do cyclic. We know that it's reading in 500 bytes, so let's do cyclic 1000. We've generated a cyclic pattern. Now we're going to run the program. We're going to paste that in, and we'll see that the program crashed, which is good. And it's crashed because it's ended up with this string. It's tried to read this essentially as an address. It's tried to return to this address. So what we want to find out is what was the offset of this address that it tried to return to. Notice that it's not in the RIP because it's 64-bit and it won't actually try to load this invalid address. But if we go and do cyclic-L and paste that in, we'll see that it's 72 bytes. So it's 72 bytes that we need to write before we'll be able to begin overwriting the instruction pointer to return to an address of our choice. And so we can see this is 64 bytes. That's roundabout matching up. There's sometimes a little bit of extra space there provided by the compiler, so you can't always just go by the size that it shows here. So we're just testing that manually, but we're still going to do this in Pwn Tools anyway. Let's copy over the Pwn Tools template that we use in all these videos, and I'll just call this exploit.py for now. Let's open that up. And again, if you watch my videos, you'll be sick of hearing all this, but we've defined our context here so that we don't need to worry about the architecture and the bits and things later on. We don't need to say whether it's a 64-bit address or a 32-bit address. We'll go and update our binary name here. We'll change our context level to debug so that we can see what's being sent and what's being received. In the background, we can set up breakpoints here if we want to break at main, which probably will want to do later, so I'll set that up now. And then we have our find IP function as well. This is going to find the offset to the instruction pointer. So at the moment this is set up to do this for a 32-bit application. So I'm just going to go and uncomment the 64-bit and I'll comment out the 32-bit. We also are going to need to change this. So let's see what happens when we run the program again. It gives us, the last thing is a question mark. So I'm going to go up here. The only thing I'm going to do is just change this to a question mark. And what's going to happen is before we even start the program that we're going to do the we're going to build up this exploit in, it's going to launch a separate process which is going to try and crash by sending in a cyclic pattern. In this case, we'll send a cyclic pattern of 1000. And once the program crashes, it's going to wait for it to crash. Once it crashes, it's going to read the core file that's been dumped, and it's going to find out it's going to find out what we just did in GDB. So it's going to come back and say the offset is 72 bytes, and that means whenever we're building up our payload, we'll just be able to say at this offset of wherever the buffer overflow is, or wherever the return address is going to be, we want to inject whatever code or whatever ROP gadgets. So I think that's good. Let me take some of this out. I'm going to do io.interactive. Just set this up ready for later. And we're not going to bother writing the payload to a file either. Okay, and I'll just comment this out. Let's just make sure that the offset is working okay first of all. So we run that. Because we've got the debug mode on, it's showing us, you can see all these debug messages here, it's showing us everything that's happening behind the scenes. So it sent off that 1000 characters, the cyclic pattern, and it's crashed the program. It's come back and said, okay, we found that the program crashed, and the four characters that ended up in the RSP were at this offset, 72. Okay, so now let's talk about how we're actually going to exploit this challenge. So because we can't execute code in the stack, we can't simply just use shellcraft and inject some shell code. Whatever we inject is not going to be executed. We need to use some RUP gadgets that are already in the program and then return to libc. Now the problem is, in previous challenges where we've done this, quite often we have an address that's leaked to us, or we have a printf format vulnerability where we're able to actually leak an address from the stack and then calculate our offsets from there. We don't have anything like that in this program. We've got very little to play with here, but we do have some function calls. So we have puts, which is being called at the beginning of the program. So let's go and look at let's have a look at the got.plt here. So essentially what's going to happen is whenever this program runs, the first thing it's going to do, it's going to do this puts call, and the puts call is going to reach out to libc, and it's going to populate the address in the global offset table. So it's rather than packaging this puts code in with the binary, it's going to rely on the puts version that you have on your system, which will vary from system to system depending on what version of libc you have. And whenever it calls that, it's going to look to libc and say what's the address of puts, and then it's going to put that address in the global offset table so that anytime in future it needs to call it, it just knows, okay, we just need to go to this address that we have saved. So because this is populated at the beginning of the program, by the time we get to our fgets call, we can already grab that address from the got table. So we can actually use puts to print out that address, and then we'll be able to calculate our offsets from there. So let's have a look here at puts. If I just highlight that, you'll see there it takes in we have the int in the EAX and then the char pointer in the RDI. So what we need to do is we need to pop a value into the RDI. So we're going to want to pop the the got.puts address into the RDI, and then we're going to want to call puts to put that out to the screen. Hopefully that makes sense. Maybe didn't explain it too well. Let's go and start putting this together, and it'll hopefully make more sense. So one thing we're going to need is pop RDI. So we could actually find that in Geardra. I'm going to use Ropper to find it. So we'll do Ropper -- file and then ropme, and then I'll search for pop RDI. We'll find perfect. There's a gadget there. It's exactly what we needed. Sometimes you might not find pop RDI. You'll find a series of gadgets that chain together. So you'll have like pop RDI, pop RSI, pop or pop RDI, pop R15 or something. So in that case, we could use that gadget. We'll just need to bear in mind that we'll need to inject some kind of junk value so that it doesn't interfere with the rest of our payload. But in this case, this is actually perfect for us. Let's go ahead and say that the pop RDI address is equal to, and then we can just paste that in. Later on, we'll improve this script so that we don't actually need to go and manually find these addresses. But this will do for now. It's good for demonstrating manually first of all anyway. I'm just going to also try and improve the formatting of this a little bit. And okay, so this flat function is going to take an arbitrary number of arbitrarily nested lists, tuples, and dictionaries. It'll find every string and number inside of them and flatten them out. So because we've defined this context up here, whenever we put in addresses and strings and things in here, we don't need to worry about specifying whether it's P64 or P32, or if we were doing shellcode, we wouldn't need to worry about specifying whether it's Linux or Windows or little endian, etc. So that's in there. So the first thing that we're going to want to do is pop the RDI, which we just found the gadget for. And then what do we want to pop into the RDI? Well, we want to pop in the got.puts address, and we could go and find that manually. I'm just going to do elf.got.puts. If you wanted to, you can go through here and just print out, just go and do print or pretty print. In fact, let's do it quickly. Let me comment that out, and let's run this and just do pprint elf.got. We run that, and you can see here then we've got our puts, we've got our fgets, we've got our fflush, etc. If if GOTS hadn't already been called and this hadn't the address hadn't been put into the table, then into the global offset table, then we would need to call it first before we'd actually be able to do this. But in this case, it doesn't actually matter because we're going to be calling, so we're putting the elf.got.puts address into the pop RDI, and then we're calling elf.plt.puts. So in calling elf.plt.puts, that'll actually populate the GOT anyway, and that'll print out address. So that's fine. It's going to put out the address to screen. But after that, we don't just want the program to exit like it does naturally. We want to go back to our main method. So we can do elf.symbols.main. And this should be good for our payload. So we want to send the payload. I'll uncomment this. We're sending it after the question mark again. And then we'll just do IO interactive now. So let's run through this and see what happens. So we can see that we've leaked an address. That's awesome. So we're going to want to go and format it and have a better look to verify that it's okay. But we can see that that's the address that we have here: F0D5 26cc, etc. And it's gone back to the main method as well. So we can then continue. Now that we've leaked that address, we can go back and actually do the second part of our exploit. So this exploit is going to have two payloads. The first one where we're actually leaking the address, and then we'll calculate our offsets to the libc functions that we're interested in, like system and like the bin sh string. And then we'll be able to, because we're back in the main function again, we'll be able to run another payload on it. This time our payload will be to actually gain a shell. Okay, so just to deal with the format in here as well, we're gonna receive here, just to receive the new line before we get our, you can see there's a new line here before we get our actual address. We need to read that in, and then the address we want to format, so we'll say our got puts address is equal to unpack, and then we can pass in io.receive. This will be the next part that it'll receive. We're going to take the substring, so we'll take the first 6 characters, and then we can do .ljust by 8 and null bytes. If we do this, and then we'll say info leaked puts leaked got puts is equal to percentage hash x, and then pass in the got puts. So let's just test that out quickly. And there we have an address. So is this the got puts address? Let's find out. We've already set up the breakpoint up here at main. So if I run this again, and this time just pass in GDB, we'll see we've got to our breakpoint. We need to continue because it's not actually leaked the address yet. So we'll hit C to continue. You'll see that it's hit a breakpoint again because we set it to go back to the main function at the end of the payload. So it's gone back to main, it's hit a breakpoint, but this time we have this leaked got puts address. So we can go here and we can say X and then paste in that address, and we'll see, yep, that's the address of puts. We could also go and say X system, and there's our libc system. We could do search, let me do search help, search dash S for strings. So we can do search dash S and then say bin slash sh. And we can go and grab our offsets here as well. We can actually subtract offsets and calculate the offsets we need here as well. But I'm going to go and do that elsewhere in a second to get the other addresses that we need. So let's close this down for now. So a typical way I look for offsets is using LDD first of all. Pass in ROPME. We'll get our libc library, and we can then we can do a lot of different things here to grab this address, but I'm going to do readelf-s, and then we can do that again and grep out whatever functions we want. So we want to grab the system function, and this is the offset to system. Oh, we also need our puts, the puts offset. Well, we don't really need it. We could calculate the offset to system from here, but essentially we know the offset of puts, so we can say if we subtract this from the address that we've leaked, we'll be at the base of libc, and if we're at the base of libc, we can add the offset of the system function, and then we'll be at system. So if I go, let me copy this, as our puts function, or puts offset should I say, and then we'll say that the libc base is equal to our got puts minus the offset of puts within the library, and then we can say, in fact, let's actually print that out as well. Libc base, and then we can say system is equal to libc base plus the offset of the system function that we just found. So that was right here. And then also we want the string bin sh, so we'll say bin sh is equal to, again, libc base this time. So we can find it plenty of different ways. I'm going to do, actually just keep that while I have that there. So I'm going to grep bin /sh, but instead of readelf, I'm going to use strings -tx, is it? Yeah, there we go. And then we can just copy this offset. Plus 0x, and there we go. That should be good. Let's print these out as well, and we'll go and verify them before we test this out. So there's our system. There's our bin sh. Let's run this again with GDB. We want to continue past our first breakpoint. Oh my god, the snapping it's so bad. Okay, continue, and we get to our breakpoint. We've got some different addresses here, so we already know that the puts is right. Let's take a copy of the libc base. We can do x. Okay, that doesn't really show much of interest. Let's do the same with system. So there we go, libc systems. We know we've calculated that correctly. We can do it again with the bin sh. And again, doesn't really show much of interest, but if we do x over s, we'll see that, yeah, that's bin sh in memory. So we've calculated our addresses properly. Now we just need to do another ROP chain to send these off. So I'm going to copy this payload. We're just going to do quite a similar one here. Copy the payload, and we're going to be using pop RDI again, but this time instead of popping in the puts addresses, we're going to pop in the bin sh address, and then we're going to call system. So we've got the system address as well. We're providing the bin sh string first, putting it into the RDI, and then the system call will look in the RDI to see what the parameter is. And I think that should be good. We need to send that off. In the previous case we waited for this question mark, but because we've just jumped back to the main method and done the IO receive there, that's not gonna happen. So we just want to say, we just want to send the payload this time. So we'll just do send line payload, and then go to IO interactive, and hopefully we'll have a shell. Let's test this out. So we run that, switch into interactive mode, doesn't say end of file, which is good. If we list the files there, we can see that, yep, we've got a shell, and that appears to have worked for us. So now we need to go and test this out against the remote server. As we know from previous challenges, the offsets are going to vary from system to system depending on what version of libc is there, so we need to go and try and identify the correct offsets to use this remotely. So let's go launch a server, and we can copy this address. Because we're using this template that we have, we can just pass in remote here. You see you can pass in remote in the server and the port. We don't actually need to change anything in the code, which is handy. So we'll just do Python exploit remote, paste that in, remove the colon, and send that off. And you'll see that it sent all that off, it's leaked the addresses, we've got an end of file, so we don't actually have a shell. So what we need to do is go and have a look at the leaked address. If we take this, as we have done in some previous challenges, to this libc database, and then, because it's basically only the a few of the bytes which are different, you can use these offsets to calculate the libc version. So if I was to just put in here puts you don't need to specify. If you just do puts, you don't actually need to specify the full thing. You see, we get not found. Sorry. So this took me a little while to to work this out. I was trying to leak other addresses instead of puts to see if there was an issue here. It turns out that based on some forum hints that I found, that the libc version that was used in this challenge actually is no longer in the libc database. So I did identify the correct version, which was in fact, let's go back, show all libs. The correct version, I only found this out after actually solving the challenge and getting into the server, and I went and checked the libc version. It was 2.23, but Ubuntu 9, and yeah, it's not here. So the way that I actually found the offset was from a previous write-up which had the offsets in them, which I kind of wanted to show how to actually calculate this. But I'm not actually too sure myself what's the best way if the libc is not available here. I tried to go and find a libc file to test locally, and I was only able to get the actual source code, not the actual libc.so file, which I couldn't work out how to get the offsets from. So if anybody has any ideas as to how do you find the correct version of libc, and how do you get the correct offsets in the case that the libc version is not available in this database, I'd be interested to know if that'd help me out for some future challenges maybe. But in this case, I think that previously this was available in the database, this libc version, so it's more a fact of that the challenge is not, the challenge is broken, but it's an older challenge that it's not as easy to solve now based on the libc version. So I'm going to go back and just put in the correct offsets here based on other write-ups, because this is an older challenge. So our libc, this is the offset to get back to the libc base from got_puts, and then our system address is the offset for that, and then our bin sh, this is the offset for that. And now if we run this again against the server, you'll see there we can list the files. We're logged in as root. We could do ldd-version, and we'll see here then the libc version, 2.23 Ubuntu 9, which isn't available in that database. I did actually try some other tools as well, but I ended up just wasting so much time trying to find the correct libc version that I was just like, I could be spending this time actually learning, I think, more about binary exploitation rather than just searching out the libc versions. So let's go and automate this a little bit more with some ROP objects as well. We'll also, after that, we'll import the local libc library. Let me actually just go and let me change these offsets back. We'll just work with the local version here. After that, we'll import the local libc library here as well, which can help us with getting some of these offsets so we don't even need to search for them. So first of all, we'll create a ROP object. So I'm going to say ROP is equal to ROP, and then we'll pass in the elf. We can find our pop RDI gadget instead using ROP.findGadget. And we see this function here, it takes in the instructions. So we pass in a list, so we'll say pop RDI and return. And then we want to grab the first element it finds, so it might find multiple gadgets, so you just need to select the index as well. So that means we don't even need to go and find the offset for it. And for our payload, what we can do here is say ROP.raw, and then in fact we could actually probably just do we could probably just call, let's do ROP, I'm going to do ROP.puts, and then I'm going to just try and put the elf.got.puts, and then let's try and do ROP.main, and then at our offset we'll just say we're sending off this ROP.chain, just going to convert it into the raw bytes, and hopefully that'll work for us. In fact, let's do prettyprint rop.dump. Let me comment out some of this for now. Just interested to see how this looks. So essentially, as long as the function is resolvable, this rop it should be able to find it here for us. Even if there was a custom function, we might be able to just say rop.call. Let me have a look at that. Param resolvable. So add a call to the rop chain, and resolvable is a value which can be looked up via resolve or is already an integer. So we could also use that as well, passed in a list. Let's try and run this. Python exploit. And yeah, so we've dumped that out, and it's basically built that gadget for us, right? So it's popped the it's got the pop RDI gadget, so we actually didn't even need this at all. We've not actually used this. In fact, let me comment that out for now. It's found the pop RDI gadget, and it's chained that then with the got.puts, which is put in the RDI, and then it's called puts, and then it's going back to the main method. So that's looking good. We'll send that off. Let's actually, I'll put that back a second. Let's just test this as it is then with that change that we've made, just to see if that works. Switching to interactive mode. Yep, that worked fine. Awesome. So in terms of these addresses here, what I'm now going to do is load in the libc library. So let's go back to the start here. I'll do libc is equal to elf, and then we need to pass in the location of it. So ldd ropme. We can pass this in. The cool thing about this is that if we wanted to find the offset for the server version, we could literally just download different libc libraries and then loop through and test changing this, and then we won't need to worry about all the offsets and things like that. It'll just be, this is the only thing that will need to change between the systems that we actually test the exploit on. So we define libc there. We get our got puts address back, and what we can say here then is instead of saying libc base, what we'll say is libc.address, and that's going to set the base address of this binary that we've loaded in to the address of the libc base. What we can also do as well, rather than putting in this offset manually, this is where we'll say libc dot symbols dot puts, and there's our libc base address, and then our system. Well, for system and bin.sh, actually we don't even need to call these at all here, because we're going to be able to, we can create now a rop object with the libc, right? So we've already used our previous rop object. Let's overwrite it with rop and then pass in libc, and then rather than doing all this stuff here, we can just say rop.system, because it's going to be able to resolve system. It's going to know what the address is of it. And what do we want to give it? We want to give it the bin.sh, so we can search for this. We'll do libc.search, and then just give it the string that we're looking for, which would be bin.sh. And then when we get down to our payload here, again, we can just do this the same as the previous one. So we'll just do rop.chain. We don't even really need this here. We could just put this directly in as the payload, right? So we could, well, I'll just leave that as it is. It doesn't really make much of a difference. But let's test this out. We could also, if we wanted to print this as well, we'll do pprint rop.dump. Let's run that again. Okay, so we've got our shell again. We can list files, that's great. And if we go and actually have a look at our debug info here, we'll see that we got the libc base. It then calculated the system. So we have our first payload here, which is the leaking the got.puts address. And then once we've calculated the libc base and assigned that to the binary, we can then just call rop.system and pass in the string that we're searching for, and it's built that rop chain for us. It's sent that off, and again got us a shell. So that's probably I think the easiest way that you could actually do this challenge if you didn't want to do things manually. And again, then if we had a local copy, so if this libc version was here, all we'd have to do is download that and then say that we're loading that in, and it'll find the correct offsets. We'll just run it against the server. And I think that's about it. So I'll comment these scripts pretty well, and then put them up on the GitHub so that you can check them out. The template's up there as well, so you can use this template for any challenges that you're working on yourself. But I hope you've enjoyed this video anyway. Any questions, comments, leave them down below. Thanks.